On April 17, 2025, a groundbreaking discovery was made regarding the exoplanet K2-18b located approximately 124 light-years away in the constellation Leo. This breakthrough, driven by data from the James Webb Space Telescope JWST, has ignited excitement in the scientific community as researchers reported the detection of significant concentrations of dimethyl sulfide DMS and dimethyl disulfide DMDS in K2-18b's atmosphere, molecules that on Earth are typically produced by biological processes, predominantly by marine microorganisms such as phytoplankton. Key findings: 1. Detection of sulfur compounds. The JWST observed K2-18b during its transit across its parent star, capturing a significant amount of data that indicated the presence of DMS and DMDS. The levels detected on K2-18b are estimated to be over 10 parts per million, which is thousands of times higher than what is usually found on Earth, where these compounds rarely exceed 1 part per billion. This marks the first detection of such gases on an exoplanet. 2. Characteristics of K2-18b. K2-18b is classified as a Hycean planet, which suggests it is larger than Earth and likely has a hydrogen-rich atmosphere alongside vast oceans. With a mass approximately 8.6 times that of Earth and a diameter 2.6 times greater, K2-18b orbits a cool red dwarf star within the habitable zone where conditions may be suitable for liquid water to exist. 3. Statistical significance of findings. The observations currently meet the 3 sigma threshold, indicating a mere 0.3% chance that the results are due to random noise. However, the scientific community typically requires a 5 sigma threshold for definitive confirmation, implying that further observations, estimated at an additional 16 to 24 hours of JWST time, are necessary to solidify these findings. Perspectives in the scientific community. Cautious optimism. Lead researcher Niku Madhusudhan from the University of Cambridge expressed that this discovery could bring humanity closer to understanding whether we are alone in the universe. However, he and other scientists stressed the need for skepticism and additional validation to confirm the presence of life. Skepticism and alternatives. Some researchers remain cautious about jumping to conclusions. For instance, Raymond Peary-Humbert from Oxford University has argued that K2-18b may be too hot for life, with the possibility of molten oceans instead of hospitable environments. Similarly, Sarah Seeger from MIT pointed out other celestial bodies such as Mars and Saturn's moon Enceladus that might have a higher potential for supporting life. Timeline of K2-18b observations. 2015. The exoplanet K2-18b was first discovered. 2023, initial observations by JWST detected methane and carbon dioxide in its atmosphere. 2025, further observations revealed stronger evidence of DMS and DMDS, spurring current discussions about the potential for life on K2-18b. Implications for astrobiology. The identification of DMS and DMDS adds to the growing catalog of potential biosignatures that could indicate microbial life in extraterrestrial environments. DMS, for example, is a compound exhaled by marine phytoplankton on Earth and is associated with various biological processes. The discovery of these compounds on K2-18b, if confirmed, could suggest the existence of a thriving microbial ecosystem in its vast oceans. Future directions. The JWST was designed for this type of measurement. Yet even more advanced telescopes are on the horizon. Planned observatories like the Habitable Worlds Telescope and the European Extremely Large Telescope may provide the capability to study smaller, cooler planets with richer spectra, further expanding our understanding of possible biospheres. As scientists continue to analyze the data from K2-18b, the implications of these findings could redefine our understanding of where and how life may exist beyond Earth. Researchers are poised at a pivotal moment in the search for extraterrestrial life, with K2-18b standing as a prime candidate for further exploration. In conclusion, the recent findings regarding K2-18b represent a significant milestone in the ongoing quest to determine whether we are alone in the universe. As further observations are conducted and data is analyzed, the potential for confirming the existence of life on this distant exoplanet moves closer to reality, igniting hope and curiosity about the possibilities that lie beyond our solar system. The recent detection of potential biosignatures on the exoplanet K2-18b has stirred excitement and debate within the scientific community, presenting both promising implications and notable counterintuitive findings. Key findings and data. 1. Detection of sulfur compounds. The James Webb Space Telescope JWST has identified significant concentrations of dimethyl sulfide DMS and dimethyl disulfide DMDS in K2-18b's atmosphere. While these compounds are associated with biological processes on Earth, primarily produced by marine microorganisms, their levels on K2-18b are reported to be thousands of times higher than those found on Earth. This raises the possibility that a microbial ecosystem may thrive in its oceans. 2. Characterization of K2-18b. K2-18b is a Hycean planet larger and more massive than Earth, with a hydrogen-rich atmosphere that could support vast oceans. It orbits a red dwarf star within the habitable zone where conditions might allow for liquid water. 3. Statistical significance. The findings currently meet a 3 sigma threshold, indicating a 0.3% chance that the results are due to random noise. However, the scientific community typically requires a 5 sigma threshold for definitive confirmation. Additional observations are anticipated to strengthen this data. Common themes across sources. Cautious optimism. Researchers express excitement over the findings yet stress the importance of skepticism and further data collection to confirm the presence of life. Potential for life. The prevailing hypothesis is that if DMS and DMDS are confirmed, it could indicate microbial life. However, the possibility of these compounds arising from non-biological processes necessitates further investigation. Differences in perspectives. Skepticism. Some scientists argue that K2-18b may be too hot for life, with conditions possibly leading to molten oceans. Others believe that celestial bodies like Mars or Saturn's moon Enceladus may have a higher chance of supporting life. Counterintuitive information. 1. High concentrations of biosignatures. The detection of DMS and DMDS in concentrations over 10 parts per million is a significant anomaly compared to Earth's levels, which rarely exceed 1 part per billion. This raises questions about the environmental conditions on K2-18b that could lead to such high concentrations, suggesting that life could thrive under conditions we typically associate with inhospitable environments. 2. Hot environment and life viability. The belief that K2-18b might be too hot for life contradicts the traditional understanding that life requires relatively stable and mild temperatures. The notion that life could exist in what would be considered extreme heat challenges are preconceived notions about the conditions necessary for life to flourish. 3. Biosignature versus non-biological processes. The potential for DMS and DMDS to be produced through non-biological processes complicates the narrative. While these compounds are typically associated with biological activity on Earth, their presence in an alien environment may not necessarily indicate life, showcasing the complexity and unpredictability of astrobiological research. For unpredictable chemical processes, the possibility that previously unknown chemical processes could generate these biosignatures adds an additional layer of complexity. This suggests that our understanding of chemistry in extraterrestrial environments is still incomplete, and what we consider biosignatures could arise from non-living processes. 5. The role of future observations. The need for 16 to 24 additional hours of JWST observations to reach the 5 sigma threshold exemplifies the cautious approach of the scientific method. This indicates that significant discoveries often rely on extensive validation, challenging the notion that groundbreaking findings can be declared immediately upon initial observation. In conclusion, while the findings related to K2-18b present a thrilling prospect in the search for extraterrestrial life, they also highlight the need for careful consideration of alternative explanations and a deeper understanding of the conditions that could allow life to exist in environments previously deemed uninhabitable. The recent findings regarding exoplanet K2-18b, particularly the potential detection of dimethyl sulfide DMS and dimethyl disulfide DMDS, have ignited significant interest in the astrobiological community. While the mainstream media has highlighted the excitement surrounding these findings, there are several critical nuances and implications that many may overlook. Understanding these can provide deeper insight into the implications of the research. 1. Statistical significance and the 5 sigma threshold. The report indicates that the findings related to DMS and DMDS meet the 3 sigma threshold, suggesting a very low probability, 0.3%, that the results are due to random noise. However, many in the scientific community emphasize the necessity of achieving a 5 sigma threshold, 0.00006% probability, for a definitive claim of discovery. This cautious approach is significant because it underlines the importance of rigorous scientific validation. The additional 16 to 24 hours of observations needed to achieve this threshold underscore the fact that while the current data is promising, it is not yet conclusive. 2. Potential non-biological processes. While DMS and DMDS are typically associated with biological processes on Earth, the possibility of these compounds arising from non-biological processes cannot be ignored. Some researchers have raised concerns that exotic photochemistry or geological activities could also produce these gases. This highlights the need for a comprehensive understanding of K2-18b's atmospheric and geological context. The implications of such alternative pathways could fundamentally alter our interpretation of the data and the likelihood of life existing on K2-18b. 3. The role of Hycean planets. K2-18b is classified as a Hycean planet characterized by a hydrogen-rich atmosphere and potentially vast oceans. This classification is significant as it expands the criteria for habitability beyond the traditional Earth-like models. The concept of Hycean worlds suggests that life could potentially thrive in environments vastly different from those on Earth. This opens up new avenues of exploration in the search for extraterrestrial life, prompting scientists to re-evaluate what conditions might support life. 4. Cautious optimism versus skepticism. The discovery has elicited a mix of cautious optimism and skepticism among scientists. While some researchers like Niku Madhusudhan emphasize the significance of these findings as the closest indication of extraterrestrial life, others such as Raymond Peary-Humbert argue that K2-18b's temperature may render it inhospitable. This divergence in perspectives highlights the ongoing debate within the scientific community regarding the parameters defining habitability, and it's crucial for public understanding that the scientific process is inherently iterative and skeptical. 5. Historical context of exoplanet research. The timeline of discoveries related to K2-18b illustrates a progressive understanding of its atmospheric composition. The initial discovery in 2015 and subsequent observations in 2023 that detected methane and carbon dioxide laid the groundwork for the recent findings. This historical context is essential for recognizing the incremental nature of scientific discovery, where each observation builds upon previous knowledge. It also serves as a reminder of the patience required in scientific inquiry, especially in fields as complex as astrobiology. 6. Broader implications for the search for life. If confirmed, the presence of DMS and DMDS could have far-reaching implications for our understanding of life in the universe. It could suggest that life may not be as rare as previously thought, particularly in environments vastly different from Earth. This shifts the paradigm of astrobiology, encouraging researchers to explore more diverse planetary systems and environments. The idea that microbial life could exist in oceans beneath the clouds of Hycean planets could redefine our search strategies and the technologies we develop to seek out extraterrestrial life. 7. Technological advancements and future observations. The role of the James Webb Space Telescope JWST is central to these discoveries. Its advanced capabilities allow for more detailed atmospheric analyses than previously possible with earlier telescopes. Future observatories like the Habitable Worlds Telescope and the European Extremely Large Telescope are poised to enhance our understanding further. The technology and methods used in these observations will be critical in distinguishing between biological and non-biological sources of the detected compounds. Conclusion. While the excitement surrounding the potential signs of extraterrestrial life on K2-18b is palpable, it is essential to approach these findings with a nuanced understanding of their implications. The statistical significance. The potential for non-biological processes, the classification of Hycean planets, and the diverse perspectives within the scientific community all play a crucial role in interpreting the results. Moreover, the historical context of exoplanet research and the advancements in technology remind us that scientific discovery is a complex iterative process. Ultimately, the ongoing exploration of K2-18b may not only shed light on the existence of life beyond Earth but also redefine our understanding of what constitutes a habitable environment in the universe. 1. Discovery of biosignatures. The recent findings from the James Webb Space Telescope JWST regarding the detection of dimethyl sulfide DMS and dimethyl disulfide DMDS in the atmosphere of the exoplanet K2-18b represent a significant breakthrough in the search for extraterrestrial life. These gases are primarily produced by biological processes on Earth, particularly by marine microorganisms like phytoplankton. The concentrations of these compounds observed on K2-18b are thousands of times higher than those typically found on Earth, raising the possibility of a thriving microbial ecosystem in the planet's oceans. This marks the first detection of such biosignatures on an exoplanet outside our solar system, igniting excitement and debate within the scientific community about the potential for life beyond Earth. 2. Characteristics of K2-18b. K2-18b is classified as a Hycean planet characterized by its size, 8.6 times the mass of Earth and 2.6 times its diameter, and its hydrogen-rich atmosphere. Orbiting a cool red dwarf star within the habitable zone, K2-18b is believed to have a vast ocean capable of supporting life. The planet's unique characteristics make it a prime candidate for further exploration and study, as researchers assess its potential to harbor life. The classification of K2-18b as a Hycean world is significant because it broadens the scope of environments considered suitable for life, moving beyond traditional Earth-like criteria. 3. Statistical significance and caution. The current findings meet a 3 sigma level of statistical significance, indicating a 0.3% chance that the results are due to random noise. However, the scientific community generally requires a 5 sigma threshold for definitive confirmation of discoveries. Researchers estimate that additional observations totaling 16 to 24 hours could help achieve this benchmark. Despite the promising results, scientists urge caution, emphasizing the need for further data to confirm the presence of life and the potential for non-biological processes to produce the observed gases. This highlights the importance of rigorous scientific validation in the field of astrobiology. 4. Diverse perspectives on habitability. While the discovery of biosignatures on K2-18b is groundbreaking, it has also sparked diverse perspectives within the scientific community regarding the planet's habitability. Some researchers express skepticism about the potential for life on K2-18b, citing concerns about its temperature and the possibility of molten oceans. Others argue that the detection of biosignatures is a significant step toward understanding the conditions under which life could exist on other planets. This ongoing debate reflects the complexity of astrobiological research and the need for interdisciplinary collaboration to address the myriad factors that influence the habitability of exoplanets. 1. The wow. Signal 1977. In 1977, a strong radio signal was detected by astronomer Jerry R. Emmon while working on a SETI project at Ohio State University. The signal, which lasted 72 seconds, was so unusual that Emmon noted "wow" next to the data printout. The signal originated from the direction of the constellation Sagittarius but has never been explained or detected again, leading to ongoing speculation about the possibility of extraterrestrial intelligence. 2. Mars meteorite ALH 84001 1996. In 1996, NASA announced that a meteorite found in Antarctica ALH 84001 contained structures that resembled microscopic fossils of bacteria, suggesting that life may have existed on Mars billions of years ago. This claim generated intense debate among scientists, with some supporting the idea of Martian life while others argued that the features could be the result of non-biological processes. The excitement surrounding the meteorite provided a significant boost to astrobiology research. 3. Tabby's star KIC 846-2852. Discovered in 2015, Tabby's star exhibits unusual dimming patterns that have puzzled astronomers. Some scientists initially speculated that these fluctuations could be indicative of an alien megastructure such as a Dyson sphere built to harvest energy. Subsequent research suggested that the dimming could be caused by a swarm of comets or dust. But the star remains a subject of intrigue in the search for extraterrestrial life, illustrating the complexities of interpreting astronomical data. The recent detection of potential biosignatures on the exoplanet K2-18b, located 124 light-years away, has ignited a wave of speculation about extraterrestrial life. Researchers utilizing the James Webb Space Telescope JWST have identified significant concentrations of dimethyl sulfide DMS and dimethyl disulfide DMDS in K2-18b's atmosphere, compounds typically associated with biological processes on Earth. This discovery could represent a turning point in our understanding of life beyond our planet. Future outlook and predictions. 1. Confirmation of life. Within the next few years, additional observations from the JWST or other advanced telescopes may provide the necessary data to confirm the presence of DMS and DMDS at a 5 sigma significance level. If these biosignatures are verified, it would radically shift our perspective on life's existence in the universe, indicating that microbial life could thrive in environments vastly different from Earth. 2. Technological advancements in astrobiology. The success of the JWST in detecting potential life signatures will likely spur the development of more sophisticated observational technologies such as the Habitable Worlds Telescope and the European Extremely Large Telescope. These instruments will enable the exploration of smaller, cooler planets and enhance the ability to detect a wider range of biosignatures. 3. Focus on Hycean worlds. The findings from K2-18b will likely lead to an increased focus on Hycean planets, ocean-covered worlds with hydrogen-rich atmospheres. Future missions may prioritize the study of similar exoplanets, expanding our search for life in the universe and refining our models of habitability. For interdisciplinary research initiatives, the implications of finding life on K2-18b will foster interdisciplinary collaborations among astronomers, biologists, chemists, and planetary scientists. These collaborations will enhance the understanding of life's potential forms, the chemical processes that can sustain life, and the environmental conditions necessary for habitability. 5. Increased public interest in funding. A confirmed biosignature on K2-18b would capture the public's imagination and likely lead to increased funding for space exploration and astrobiology initiatives. Governments and private organizations may invest more in missions aimed at discovering life beyond Earth, leading to a new era of exploration. 6. Ethical considerations and planetary protection. As we move closer to potentially discovering extraterrestrial life, discussions surrounding ethical considerations and planetary protection will become crucial. Scientists will need to address the implications of contacting or studying other life forms, including the risks of contamination and the responsibility to preserve extraterrestrial environments. 7. Cautious optimism and scientific community. while excitement abounds regarding the findings on K2-18b. The scientific community will continue to approach these discoveries with caution. Researchers will conduct rigorous testing and analysis to rule out non-biological explanations for the detected compounds, ensuring that any claims of extraterrestrial life are substantiated by robust evidence. 8. Exploration of non-biological mechanisms. Research will also explore the possibility of non-biological mechanisms producing DMS and DMDS in environments like K2-18b. Understanding these processes can enhance our comprehension of planetary chemistry and the diverse conditions under which life might arise. 9. Potential for discovering intelligent life, if microbial life is confirmed on K2-18b. Future missions might target other exoplanets and similar habitable zones with the aim of finding more complex organisms or even intelligent life. This pursuit could redefine humanity's place in the cosmos and lead to profound philosophical and existential inquiries. 10. Long-term implications for humanity. The discovery of life beyond Earth would have far-reaching implications for humanity's understanding of biology, evolution, and the nature of life itself. It could challenge deeply held beliefs and inspire a new generation of scientists, thinkers, and explorers dedicated to uncovering the mysteries of the universe. Conclusion. The findings regarding K2-18b represent a significant milestone in the search for extraterrestrial life. As researchers continue to analyze and confirm these results, the coming years hold the promise of groundbreaking discoveries that could transform our understanding of life in the universe. The journey toward confirming life beyond Earth is as important as the discovery itself, as it encourages scientific inquiry, technological innovation, and a broader perspective on our place in the cosmos.